This video is about oil, about the way it is extracted from the earth or produced. Some say that it's easy to produce oil. All you do is go to the remote and sometimes very difficult to reach places on earth, even the high seas, deserts, icelands, jungles where no one has been before. Drill and you will get oil, eventually. Just open the tap and it flows. If it were only that easy. Keeping up with the behavior of all the wells and complex surface equipment makes controlling an oil field a tough job indeed. Predicting how a well is behaving underground is already a very difficult job, since we can't see what is happening several kilometers into the earth. It's like flying an aeroplane in the night or the fog. You know that there is ground, but where is it? You can't rely on your senses. You'll have to depend upon your instruments, your equipment, to fly and land the plane safely. As for oil wells, let us assume we found oil somewhere and that we can produce it somehow. Then, by using new technology, the production rates can be much improved.
We know that we can produce more oil from existing reservoirs. We call this production potential. For the Shell Oil Group worldwide, this is equivalent to about 900,000 barrels per day. That's a medium-sized tanker. Using this technology, we believe we could produce about 250,000 barrels of oil off that. That's about a third of a tanker. That's what it's all about. Improving your profitability by increasing your production.
Flying a plane. It's impossible nowadays without the instruments, all the seemingly hundreds of gadgets that help a pilot fly the machine. But only some of them are necessary to keep the plane in the air. The rest are there to trim the plane, constantly testing and retesting, making adjustments. They optimize the process of flying, thus helping the pilot to concentrate on the central issue, to get the passengers to their destination on time, comfortably and safely. Operating an oil field seems a lot simpler than flying a plane, but is that true? For instance, you need extensive information about your wells and facilities too before you can maximize your production. You need to know how the well is constructed, how deep is it, how large is it. You need to know the oil production rates and how much gas and water are produced with the oil. You need to know the temperatures and pressures of the production stream. And you need to know it all the way, from the reservoir to the export tanker. Because as the professionals say, you can't optimize it if you can't measure it. Last but not least, you need equipment, instruments, and trained people to safely optimize your production. Shell has been working hard on systems that help optimize the production of oil and gas wells. Nowadays, the instruments that are constantly sensing the pulse of the process are controlled by a computer, which diagnoses the information and takes proper action when any undesired or unwanted behavior takes place. These systems are called computer-assisted operations, or CAO systems. They are designed to assist the production field operators in performing their jobs through central monitoring and control of field equipment. These systems are being used by Shell to improve operations that involve well testing, beam pumping, electric submersible pumping, and gas lift.
As part of the drive to increase the use of computers in oilfield operations to optimize production, Shell Oil in the States developed a software system called the Shell Oil Foundation software to use real-time data in this application. They then married this to an existing Hewlett-Packard system called Real-Time Application Platform, and we came up with a system called SOFT's RTAP. Our business now is to install this technology throughout the Shell Group.
To put their new system together, Shell found a partner in Logica. That company combines domain knowledge with the necessary information technology and project management skills, enabling timely delivery of oil production information technology, or IT systems. Logica configured an integrated SOFS RTAP-based supervisory control and data acquisition system for monitoring and control of several of Shell's fields. Logica, for instance, enabled a smooth implementation of SOFS RTAP CAO systems with PDO in Oman. The technology supports the field operators with technical tools to improve monitoring, analysis and control of the fields. It helps the operators stabilize their wells and improve production at the same time. Generally speaking, it puts them in better control. One of the primary things to be controlled and optimized is their gas lift system. As in Oman, much of the oil in the Shell group is produced using the technique called gas lift. Initially, a well may produce by itself, using the energy available in the reservoir, but later on the oil needs help to reach the surface. Gas lift is used to control a well by injecting high-pressure gas into the casing annulus. The gas is allowed through valves deep down in the casing annulus, and it flows into the production tubing, mixing with the oil. This lowers the density of the flow stream of oil, thereby lowering the pressure at the bottom of the well, and in doing so yielding more production. Injecting too much or too little gas can cause problems for a particular well or even a whole system. So, controlling the wells, making the best use of limited supply of gas lift, and maximizing production from the wells all at the same time is a real challenge. Flying. Flying. It's great, especially when all goes well. But sometimes something goes wrong. Then what do you do? It's not unwelcome when you can train for the various circumstances that can occur in reality without endangering the lives of hundreds of people, including yourself. For much the same reason, Shell and Logica built a working model of a well in their Dutch training center at Noordwijkerhout and equipped it with the same kind of CAO system used in places like Oman. The model can simulate the actual behavior of a gas-lifted oil well under different operating conditions. A common problem in gas lift wells is that they can become unstable. Most instabilities are from the interaction of the tubing pressure and the casing pressure as the gas goes into the tubing through the gas lift valves. The three major variables that help to control the stability of a well are the well choke, the amount of injected gas, and the size of the gas lift valves.
So what I'm going to do, I'm going to use this model to help us understand gas lift well instability. First, we'll see what gas lift well instability is. Then we'll talk about why it's bad for our wells. And then finally, we'll talk about how we need to eliminate it from the wells and how to go about doing that. This is the tubing, which is going to bring the production from the reservoir up to the surface in a real well. And you can see in the tubing these different bubbles of gas going by. This is simulating the gas lift gas. And in the model, these bubbles actually look a lot like they do in a real well. What these bubbles do is lighten the liquid column, and in doing that, they reduce the pressure down at the bottom at the reservoir. The pressure supplied to get the gas to go into the tubing goes through this gas lift valve, and it's in a real well, it's held in the casing annulus. Okay? And the casing annulus in this case is simulated by the simple air bottle back here. This model is supervised and controlled by this Hewlett-Packard 9000 series computer. It does a really good job of controlling the model, and we've used it as a Shell standard in the group. You can see that these bubbles now are slowing down, and this kind of periodic rise and fall of injection and production is indicative of an unstable well. You can see that the liquid production in yellow is falling off to zero, and at the same time the casing pressure and tubing pressure are increasing. Now this will continue to repeat in an extremely regular, very regular cycle. That's indicative of well instability. Now that you know what gas lift well instability is, let me tell you a bit about why it's bad and why we want to eliminate it from our wells. All right? The first reason is that it reduces the production from the well. That's the main thing. The well's just going to produce less when it's unstable. The second thing is that when the well is doing this, the flowing bottom hole pressure, the pressure near the reservoir is going up and down, up and down. And this sort of cycle in pressure can result in reservoir plugging, sanding of the well, things like that. Another reason is that these slugs of liquid, when they reach the facilities, are going to play havoc with the separators downstream. And finally, the last problem is that the data quality from our unstable well is going to be just poor. So now you know that instability is bad, and we have to work on ways to eliminate it. So I'm going to show you 3 ways to eliminate gas of well instability. First, we're going to choke the well at the surface. Then we're going to change the injection gas rate. And finally, we'll change the port size in the orifice in the gas lift valve. So let me first decrease the choke at the surface. I can do that from the CAO panel right here. I'll change that wellhead choke to make it smaller. And we can see how the well stabilizes. Now what we've got is a well that will produce constantly, but will produce at a lower rate. Obviously, this isn't what we want to do for our wells. Okay, so let's try something different. What we're going to do now is we'll increase the injection gas into the well and try to stabilize the well that way. Let me do that now. And what we'll see is the gas rate will pick up quite a bit and the well become extremely stable. You can see how stable this well is. I've got a lot of gas going in the well. Over here on the screen you can see the production is nice and stable. It's nice high production, and that's good. But what we've had to do is use an awful lot of lift gas to make this happen. Most of the time we just don't have that much lift gas to go around all the wells. So what I'm going to do now is I'm going to change the port size in the gas lift valve and see if we can stabilize it that way at that lower lift gas rate. And what's going to happen is going to become stable at a lower injection rate than we had before. So we couldn't afford all that extra lift gas, and now we have an injection at a lower rate. Well, of course, because of that, we're going to have a lower amount of production. So now that you can see well instability in your own wells and recognize it, and now you also know how to eliminate it from the wells, I'd like you to think about how you can use a system like this in your own field. Remember that this system can collect and display the data as it's just done to you automatically. And it could do this whether your well or model is located right next to the system or maybe hundreds of miles away. It can also do the same thing. The system is powerful enough to be able to handle hundreds of wells. And these are exactly the kinds of things that this HP 9000 CAO system is doing around the world in the Shell Group.
In practice, you don't know which wells are unstable. Just as in the model, a CAO system in the field can help you find the unstable wells and correct them. The SOF's RTAP system in Oman can automatically detect unstable wells and perform system-wide optimization of gas injection, enhancing production in any circumstances.
Oman proved that by using this technology, they could produce more oil using less gas. A challenge now is to hold those gains. A key to that is training operators. Using the gas lift model here at the training center is a way of achieving that. Seeing is believing and leads to understanding.
The fact is, whether you fly a plane or produce a well, you need to be more than just in control. A firm hand is always necessary, but many times subtlety is best to get the most out of a plane or an oil well. The great benefit of the gas lift model built by Shell and Logica is that it helps you see the possibilities. It helps you understand your wells and visualize what the potential of CAO might be for you.
So any questions?